Let's see. So did the live stream start? Okay. Okay, good. Let's remove this Zoom meeting controls as well. Okay, great. So we can get started on time. And now finally I have the screen exactly like what you see. This was so hard to get right. Okay, welcome to lecture 6. I see fewer people than yesterday, but still quite good attendance. That's good. I don't know, maybe there's someone in the other room also interesting, overflow room. They like having a single full screen by themselves, I guess. It's a nice cinematic experience, probably. Okay, that's good though. It doesn't matter. So today we're going to finish up combinational logic. I'm going to finish up some part. It's going to be just a reminder to you, although we'll cover some interesting circuit also. And then we're going to start and hopefully finish, I don't know for sure, sequential logic design. And by the end of today, you will be able to design finite state machines that can, for example, control traffic lights and maybe even things that can do other interesting things. So everything that you see can be modeled with a finite state machine, actually, as long as you know the input states and outputs. And hopefully you will see that. This is a very powerful concept, I think. But first, we will complete combinational logic. We covered a lot of things, actually, in combinational logic in the last 2 lectures. We covered many combinational logic blocks. This is a reminder to you. I'm not going to go through this entire thing. And we covered a lot of interesting notions, SOP and POS, sum of products and products of some, standard form representations, logical completeness, and logic simplification via Boolean algebra. And basically, this is where we left off. Even though we did simplify logic, I wanted to spend some more time on logic simplification because there are many ways of doing logic simplification. Clearly, using Boolean algebra, axioms, theorems, simplification rules enable you to do it. Looking at the truth table and looking at patterns, finding patterns in the truth table enable you to do it. But of course, there are methodical ways, like starting with the sum of product form that we discussed and then reducing it in a methodical way. You can also do it that way. So there's no single way of logic simplification, actually, but some are more methodical than others. So remember, this was the full adder in sum of product form logic. This is the full adder's truth table. And this is correct. It was correct earlier also. And sum of products form says that you basically form every single minterm, and the minterms that lead to a 1 in carry I plus 1 are connected to this OR gate. Basically, the function C I plus 1 function is an OR of the minterms that lead to a 1, and sum function is OR of the minterms that lead to a 1 in the sum output. Okay, that's nice, right? So if you want to simplify this, again, you can basically start with the sum of products form that we saw, write as a Boolean equation, and basically go through Boolean algebra to simplify it. That's one way of doing it. Eventually, you'll arrive at something like this, basically. This is the simplest form you can get. The sum is an XOR, a 3-input XOR of A, B, and C in. And C out is a 3-input majority function of A, B, and C, basically. If at least 2 of A, B, C are true or 1, the output C out is 1, basically. These are actually very common circuits also. Majority we didn't look at, but clearly you can see majority function is computes the majority of an n-input function. Okay, so you can also convince yourself by looking at the truth table, right? By looking at the truth table, you will see that sum is 1 if at least, sum is 1 if an even number of C, A, and B are 1. And you can look at that. And C out, again, you can also look at it by basically, you can do the simplification by just looking at the truth table if you can observe patterns. But of course, it's very hard to do it if you have a 20 input circuit and 20 output circuit, right? Yeah, that's the difficulty, basically. Once you get to more than 3, 4, 5, 6 inputs, it becomes very difficult. So you need to really become much more methodical. Okay, so how do we simplify Boolean logic? How do you automate simplification? These are actually very, very good questions. And clearly, we discussed that original Boolean expression may not be optimal. This may be something you start with. This is a bit of a nuisance, but it's useful for people to see it, especially if they're watching on ETH video portal. Basically, you can reduce the Boolean expression to an equivalent expression with fewer terms. And we discussed why this is important, right? The goal is to reduce the number of gates, inputs, which reduces the implementation cost and potentially the latency and power. We'll see latency 2 lectures later, next Friday. But clearly, you can see that as you reduce the number of gates significantly, you can reduce the latency as well as power. And this is really the basis of what automated design tools are doing today. Let me give you the key idea of these automated design tools. They can clearly use Boolean expressions, but there's one thing, one theorem that's extremely powerful. It's called the Uniting Theorem, and it enables a systematic technique for simplification. And this is very amenable to automation. And it's best observed by looking at truth table like this. Basically, or thinking about this. Basically, if you have a function that looks like this, you can see that this function doesn't depend on B, right? It depends on A, but it doesn't depend on B, so B can be eliminated. So you can also look at it through the truth table. You can see that B's value changes within the rows where A is 1, but function doesn't change depending on the B's value. That means that the function, when the function is 1, it's not dependent on B's value, it's only dependent on A's value. That's the uniting theorem, basically. A's value does not change within the onset rows. Onset rows are rows where the function evaluates to 1, basically. And if an input, B, can change without changing the output, then that input value clearly is not needed. That's the idea of the uniting theorem. And it's also expressed by this, as you can see. That's the Boolean expression. That way you can eliminate one variable, B, and A remains. And you can do this methodically for every single variable, basically. Observe which variable doesn't matter for a given output for the onset of the function, and you can keep eliminating. That's the basis of automated design tools today. And you can imagine building tools that work on that basis, right? Okay, so, or you can do the Boolean simplification, as we discussed, right? So you can also see it over here, right? G, for example, G function here, B's value stays the same over here. When you always look at the onset. Remember the sum of products. Onset is G is 1. When G is 1, B's value is constant, A's value changes. That means that A can be eliminated, right? Because A's value changes, but it doesn't affect the output of the function. And A is eliminated, B remains, and you can see that G is B bar in this case. Or you could have figured it out by writing the sum of products form and simplifying it. And this is the sum of product form for this 2-input function. Okay, so hopefully that's clear. You can basically simplify logic in many different ways, but this uniting theorem is really the basis of many automated design tools. And this already basically says a single varying variable can be eliminated by just looking at the onset, where only one variable changes the value of the function. Okay, so let me give you another circuit. This is actually interesting. This is going to show you another way of expressing the truth table, something called don't cares, and also simplifying logic based on the truth table as well. Okay, so how many people know about priority circuits? Okay, some people, not many people. But priority circuit, basically, it has inputs. Inputs are requesters with priority levels. They request a resource, for example. It could be a bus or wire that is used to communicate. And you may have many requesters. You may have a machine learning accelerator. You may have a CPU. You may have a GPU. You may have memory. And they may have a static priority among them. Maybe a more interesting example in a self-driving car. You need to access, for example, a memory location. And there's a single bus to access a memory location. Which important accelerator should get prioritized? Well, maybe the braking system gets the highest priority. Maybe some other vision accelerator gets the second highest priority. Maybe CPU gets the third priority and GPU gets the fourth priority. So you can decide a priority level across the requesters. And outputs basically give a grant signal for each requester. Each requester has a single grant signal, as we will see. So let's take a look at a 4-bit priority circuit. This is, and I already given you the real life example. This is a 4-bit priority circuit. These are the requesters input, A3, A2, A1, A0. A3 has higher priority, and priority goes down this way. So if A3 requests let's say, resource that it wants, it should get it. And these are the grant signals corresponding to each request. And now, if you construct the truth table of this, it looks like this. Basically, if A3 is requesting, it doesn't matter what anybody else is requesting. Output corresponding to the grant signal for A3, meaning Y3, should be 1. And all of the other requesters should not be granted, meaning their corresponding outputs, Y2, Y1, Y0, should be 0. Okay? So this is a full truth table, but you can see there's some correspondence between the output and the inputs. If A3 is not requesting, but A2 is requesting, then A2 should get the circuit, should get the resource, meaning Y2 should be 1, regardless of what A1 and A0 are. That's the notion of priority, because A2 has priority over A1 and A0. If A1 is requesting and A2 and A3 are not requesting, you can see that these are the 2 rows, then it doesn't matter what A0 value is. Y1 should be 1, and everything else should be 0. And the poor A0, that's the lowest priority requester. If it is requesting and when no one else is requesting, it should get the, well, somehow it moved fast. Yeah, it should get the output, and its corresponding grant signal is asserted. And if no one's requesting, clearly, none of the outputs should be granted, right? None of the outputs should be 1. So you can see that this is a very static priority circuit. You can make it more dynamic, meaning you can change the priorities, but that changes the truth table. Now, the question is, how do you simplify it? Well, one way of simplifying this would be you write the sum of products form. That's going to be a huge equation, clearly, right? For each of the outputs, you write sum of products form for each of the outputs, and then reduce the Boolean expression. Yes, you can do that, sure. And eventually, you'll get what we will see. But another way of, I don't know what's going on. My computer is very slow here. Okay, another way of reducing this, simplifying the circuit is basically rewriting the truth table this way. Now we're introducing some new terminology, X. X means don't care. Meaning, in this case, for example, the way we read the last row is, if A3 is 1, it doesn't matter what the values of A2, A1, and A0 are, then Y3 should be 1, period. And the other output should be 0, clear, right? And again, similarly, if A3 is 0 and A2 is 1, it doesn't matter what A1 and A0 are, Y2 should be 1, and Y3, the other output should be 0. And you can basically keep doing the same thing. Now, this is a much cleaner, easier truth table. And you can just by looking at the truth table, form a circuit that looks like this. This is just by looking at the truth table. Basically, Y3 is 1 if A3 is 1. Basically, it's a direct wire from A3 to Y3 because it doesn't matter what the other output, what the other inputs are, right? Makes sense, hopefully. And another thing, Y2 is 1 if A3 is 0 and A2 is 1. And then you can keep building the other outputs from here. And this is the minimal form. Maybe you can minimize it more potentially. I don't look at it, but I believe this is the minimal form. Makes sense, right? So basically, you can use the power of logic, and you can actually first reduce the truth table from something large like that to something with don't cares. And here you can actually think about the logical implication because it's a priority circuit and don't cares make a lot of sense. So this is, we will see don't cares later on, and you'll make use of them. Whenever you see don't cares, you can actually reduce the circuit because it doesn't matter. Those inputs, if those inputs change, it doesn't matter in the end. Make sense? Okay, great. Okay, so what we will not cover is logic simplification using Carnot maps. This is actually a fun concept. It's a pictorial way of minimizing circuits by visualizing opportunities for simplification in the circuits. Unfortunately, we don't have time. And this is really not used. In a sense, it's a nice way for humans to minimize circuits, but it's not a nice way for machines to minimize circuits. And again, if you're a human, beyond 6 inputs, this also becomes not so nice, let's say, because it doesn't become easy, because you need to really think about n-dimensional ways. But again, I'm not going to go over this. See backup slides. If you're interested, you can also read this section or watch videos from these lectures from for 3 years ago in this course. Basically, we used to cover this, but I don't think it's that relevant to what is done today in practice in digital design, basically. They're just fun. Okay, so basically now we're done with combinational logic. We covered a lot of stuff, as you can see, and hopefully everything is clean. We built from transistors, and we really built some sophisticated components, and we understood how to simplify logic. But clearly, this is not enough. We need to now move to sequential logic. This is combinational logic is memoryless, but all computers have memory, as we will discuss in a little bit. But before we jump into that, basically, this is what we're going to cover today. Next week, hopefully, we'll be done with timing and verification. Okay. Okay, so I'm going to remind you of some of the assignments. Hopefully, these are actually these extra credit opportunities. If you do all of them, you'll get multiple extra credits. That's great. I'll add one more thing, which is Moore's paper. We discussed this actually, Moore's law. Moore wrote this paper in 1965. It's a seminal paper. It's an important reading. I think not many people read this sort of readings. It's only 2.5 pages, and I'll ask you to review it. Again, it's completely optional. But if you do this review, you'll get 1% extra credit. Sounds good, right? So now I gave you a good deal. 3 assignments. If you do all of them, you get 3% in the course. So if, for example, in the exam, you lose 3%, you can make up for it. with these potentially easier assignments. And I strongly recommend that you follow my guidelines for the paper review, which is on the next slide. You can find them online. There's a lecture video on how to do reviews, as well as examples that we put online. Basically, I'd like to get your opinion on what the paper is about and what you think about it. What are the strengths and the weaknesses of the paper? Does that sound good? I think it's a quite good deal because this paper is only 2.5 pages. And you know what it's about already, right? It's about Moore's law. Well, okay. And if you're interested, as I mentioned yesterday, you can look at these videos that actually talk about Moore's law and more. And this is essentially a very pictorial representation of Moore's law, in my opinion, that shows how transistor size are reduced. And these are the enablers of Moore's law, basically, these machines that enable reduce the size of the transistor. Okay, so readings, again, nothing is required, but by the end of next week, we will be done with these chapters. Today, for sequential logic, I'm especially going to go over Pat and Patel. Basically, I like Pat and Patel's way of explaining sequential logic more than Harris and Harris, but Harris and Harris is also perfectly fine. So you can learn from both of the books or none of them, just watch the lecture. Right? Okay, and next week we're going to cover some of the other things. And these are actually distributed across different chapters, as you can see in Harris and Harris. And some of these actually are not present in Pat and Patel, as you can see. So at the front of this course, at the beginning, like until lecture 10 or so, there will be a lot of readings. But after that, we're kind of going to diverge, and we will have fewer and fewer readings because the material we're going to cover actually are not in many books today. They should be, perhaps. Okay, so I think I'm going to skip these, and let's start with sequential logic circuits and design. Any questions so far? Okay, so we're going to have more fun because sequential logic circuits are actually quite fun, and this is what we will learn. Hopefully, we'll get to the end of it. We'll see. We'll see circuits that can store information, and we'll basically see the notion of finite state machines. Some really fundamental notions like state and clock. And we'll talk about asynchronous and synchronous design and how to design finite state machines. Okay, and I think the key important thing is we talked about combinational logic, but no computer can work without memory. They have to really store information from the past, basically. And clearly, if you look at these pictures, most of the computers are actually memory today. I highlighted this yesterday, right? If you look at this picture, most of the computer is memory, and internally, there's a lot of sequential logic that I cannot highlight over here as well in the processor chip. And that's true for another chip. You can see that green portion is completely caches, and there's a lot of green portions in the other parts of the chip as well. So basically, memory is most of what we design today, actually. And this is another chip from IBM, Power 10. You can see that mostly that's also memory, the green parts. But this doesn't mean that other parts, parts other than the green, other than the highlighted parts, don't have sequential logic. There's a lot of sequential logic everywhere, actually. So that's why this topic is extremely important. Without sequential logic, you cannot build computers. Basically, without circuits that can store information, you cannot build computation. Just like brains, right? Our brains are computation plus memory. Okay, basically, combinational circuit, as we discussed yesterday, its output depends only on the current input. It doesn't remember anything. But we want circuits that produce output depending on both the current input as well as past information, so that we can actually process information as that comes along, right? As a human, for example, I remember things, and that affects my information processing going into the future, right? So basically, we want circuits with memory. So the question is, how do we design a circuit that stores information? So we're going to talk a lot about storage elements, and then we're going to talk about this thing that you're looking at, which is actually a finite state machine in the end, or sequential circuit, in other words. Okay, so the question is, if you want to store information, you need to have a way of capturing data. And I'm going to give you the basic element for capturing data, which is called cross-coupled inverters. There are actually many other elements. When we talk about memory organization and technology in lecture 22 or so, we will see other technologies. But we're going to look at how to do this using CMOS technology without requiring capacitors or some other type of transistors, for example. And the basic element looks very simple. Initially, you may be surprised by it. It's called cross-coupled inverters. You can see that there are two inverters over here, right? I1 and I2, and their outputs are tied to each other's inputs. So there's a feedback loop, basically. So assume that somebody stored a Q over here. This becomes a Q bar, and Q bar turns to Q over here, and then Q turns to Q bar over here, and then Q bar turns to Q. That's what a feedback loop is, basically. this continuously keeps evaluating through the inverters and captures. It has already captured some charge, some value here, and the complement of that value over here. That's how you can store. So Q can be 1, for example, or Q can be 0. Right? Does this make sense? Maybe it looks a bit weird initially, but you can do the logic, and assuming that this was, let's say, this is 0 to start with, this becomes a 1, and this becomes a 0, and this becomes a 1. So basically, you've captured some value that cannot escape anywhere, right? As long as this is turned off, of course. Turned on, meaning powered on. We're not talking about powered off, non-volatility at this point. So basically, there are two stable states. Q can be 1 or Q can be 0. Okay? I'm not telling you how to set it yet, because this thing by itself doesn't enable you to set it. We're gonna figure out how to set it soon. Okay, these are the stable states copied and pasted from your book, and you can convince yourself these are the stable states. There is also a third possible metastable state. This is unfortunate, with both inputs oscillating between 0 and 1. If you didn't set this correctly, basically, you can get into a situation where both inputs change from 0 to 1, 1 to 0, 0 to 1, 1 to 0, and then eventually somehow randomly they settle to some value. This is something that's not desirable. We'll talk about that, especially in timing, 2 lectures later, but I'll mention that in the next element that we discuss also. Okay, does that make sense? Maybe metastability doesn't make sense, but don't worry about that right now. So basically, this is a storage element. This is a very basic storage element in CMOS, but it's not useful if you cannot set Q right. And here there's no mechanism to set Q. How do I put a 1? How do I set Q equal to 1 or Q equal to 0? There's no way, right? You have to somehow magically insert electrons there, but there's no control basically over here. So more realistic storage elements have a control mechanism for setting Q. This doesn't mean that what we discussed is actually not used. So I'm going to show you an example to motivate you, and then we're going to talk about more realistic storage elements. So we will see the RS latch soon. Sometimes it's called an SR latch, basically reset set latch or set reset latch. But let's look at SRAM. This is static random access memory. All caches are made of these elements. I'm not going to tell you exactly how it operates today. We're going to talk about it in lecture 22. But this is the cross-coupled inverter that we just saw. It just has a mechanism to set the value from here to 1 and from here to 0, for example. That's how you can store the charge. Basically, these transistors over here allow you to set the value and reset the value in this case. This is a different kind of circuit than what we're going to examine. But all of the caches and microprocessors today are built using this sort of circuit. So when people talk about 32 megabytes of cache or 64 megabytes of cache, they look like this. Basically, you have 32 mega bytes of this, and this is a single bit. Okay, so this is just to show you that what we just discussed is also used. You just need a setting mechanism. Okay, we will get back to SRAM and DRAM later. DRAM is completely different, of course, but let's not talk about it right now. So let me give you the big picture first. Today we're going to talk about latches and flip-flops. These are extremely fast elements, basically very fast parallel access, but very expensive. You will see this soon. They're going to require tens of transistors. Sometimes maybe hundreds, actually, as we will see. Basically, very expensive, as you can see. SRAM, static random access memory, is cheaper and still relatively fast. It's a bit slower, but it's cheaper. We will see how it's constructed later on, and you will see it in your labs also. It's still expensive, but less expensive. 1 bit costs about 6+ transistors. So if you go back to the picture that I showed you over here, this is 2 transistors. This is 2 transistors. These are 1 transistor each. So you have 6 transistors over here. There are other versions of it with more transistors, but we're not going to talk about them. Dynamic RAM, we talked about DRAM at the beginning of the lectures just to motivate, right? This is slower. This is what main memory is made of. Reading destroys content. We talked about refresh, needs special process for manufacturing because it's capacitor based, but it's cheap. 1 bit costs only 1 transistor plus 1 capacitor. That's why this is main memory. It's outside of the CPU almost always. And you can have many billions of bits over here. And then you go to other storage technology that's outside, even further outside. These are much slower. They have different technologies, flash memory, hard disk, tape. They're much slower. Access takes a much longer time, but they're very cheap and they're non-volatile, meaning when you turn the power off, the data stays there just because of the technology itself. That's not true for what we're going to see today, or static RAM or dynamic RAM. These are basically volatile memories. Okay, this is just to give you the big picture. Today, we're going to start with latches and flip-flops. This is where what you use to build sequential logic or finite state machines in a processor, for example, or register files. Register files are also potentially built using, especially if they're smaller size, they're built using flip-flops or latches. Okay, but we're going to leave this off to lecture 22 and beyond. Okay, so now let's look at a useful storage element that makes use of the cross-coupled inverter. We'll call it the RS latch, or kind of like the cross-coupled inverter. We're going to see something similar to cross-coupled inverter. It's the cross-coupled Nand gate, right? So you know a Nand gate. This is a Nand gate. This is a Nand gate. And this is a cross-coupled Nand gate. But we have another input here, S input, set input, and another input, R input, reset input. Now let's take a look at the operation of this, right? So, okay, I already said this. So data is stored at Q and inverse at Q bar or Q prime. S and R are control inputs. As I said, S is used to set the value Q to 1. R is used to reset the value Q to 0. So, okay, in the ideal state, both S and R are held at 1. So if S and R are both held at 1, then the output of the NAND gate is dependent on this input and this input, both of the NAND gates, right? If S and R are 1, they don't matter basically because it's a NAND gate, right? So if Q is, for example, 1, you'll get 0 at the end, and this 0 feeds back itself, and this becomes a 1 again. So basically, Q is stored as 1 in that case. Okay, that's the ideal state. But how do you set this, basically? If you want to set this, you drive S to 0 while keeping R at 1. If S is 0, what happens? S is 0, so it dominates, because this input doesn't matter at that point. So Q becomes 1. This is 1. R is 1. So this becomes 0. So nice. Now I've stored 1. Makes sense, right? Okay. That's why S is called set. If you're setting Q to 1. R is reset. If you want to reset this, meaning set Q to 0, you drive R to 0 while keeping S at 1. So let's take a look at what happens. R is 0. This doesn't matter because, again, this R dominates in an AND gate. The 0 value dominates in an AND gate. This becomes 1. This is 1. This is 1. The result is 0. Nice. It doesn't matter again. This is 1. Basically, now you've stored a 0 in Q. Okay? That's the idea, basically. That's how you set and reset this thing. Makes sense, right? This is basically pure logic, again. The difference is kind of this feedback loop that goes back, right? As long as you maintain the invariant that Q is the complement of Q bar, or Q bar is the complement of Q, there's no problem. But if you somehow make a mistake, then problems may happen. So what is the mistake? Let's talk about that a little bit. This is the mistake, basically. You should never set S and R to 0 at the same time, right? If you put S and R to 0 at the same time, so this becomes 1, right? And then this becomes also 1 because R is 0. Then you basically destroyed your invariant. How this settles actually becomes a problem. So S and R 0 is the quiescent idle state. So S and R are held at 1 is the idle state. If you set S and R to 0 at the same time, you're basically breaking an invariant. But there's another issue that we will discuss, which you may not be able to completely appreciate right now. So basically, this is the truth table of this. If S and R are both 1, the output Q is whatever the output was previous. Basically, you captured the output before, and it remains inside. If R is 1 and S is 0, Q becomes 1. If R is 0 and S is 1, Q becomes 0. That's how you write into it a value of 1 or 0. And 0, 0 is forbidden. So let's talk about this forbidden a little bit more. So why is it forbidden? There are two reasons. This is principal design, right? You should not look at the circuit and basically in the steady state, idle state, when S and R are both 1, Q should be Q bar, right? But if R and S becomes 0, Q and Q bar will both settle to 1, which breaks our invariant. This causes a problem later, which is number 2 over here. If S and R transition back to 1 at the same time, now how does the circuit settle? It becomes very interesting, right? Now you have 1, 1 over here and 1, 1 over here. How does the circuit settle? It basically settles based on the variation it's essentially the latency variation that you have inside these gates and the wires. So you don't know, basically, in the end. Because you start with something that was forbidden, that broke the invariant, right? And you basically change it to one and one, which is supposed to store what was previously stored, but you don't know what was previously stored because both of them are one. That breaks your invariant. So that makes a fundamental principle. And also, circuit-wise, we'll talk about metastability later on. But basically, the Q and Q bar start to oscillate between 1 and 0 based on the, again, variations in the circuit. At some point, one of them dominates based on which transistors inside the gates are bigger, for example. And you don't know that. This is perfect. It's purely based on manufacturing. And the circuit eventually settles to one value. It may not be the value that you want, but maybe you don't know what you want if you set SNR to 0 to begin with. Makes sense, right? This is actually, I think of this as a basic principle design, right? Principle says Q should be the complement of Q bar. If you do something that violates it, then you're definitely doing something wrong. So you should not do it. So even this number 1 is enough for me to not do this, right? But again, if you give this option to someone in the world, they will do the forbidden thing. Or they may do the forbidden thing without knowing, right? And that's not good. Basically, we do not want an element like this where somebody can go into a forbidden state and at some point, things may not work. So that's why we're going to develop something that doesn't have this problem. Okay, if you don't understand metastability, we'll talk about that later in timing. So ask me questions about metastability 2 lectures later. But assume right now that this is forbidden, but we don't want this forbidden. So how do we get rid of this forbidden? That's why we developed the gated D latch. These are interesting names. You need to remember them somehow. Basically, we want to guarantee correct operation of an RS latch. We don't want to allow someone to actually set RNS to 0 at the same time. How do you do that? Well, basically, the way you do it is basically to make sure that SNR never can become 0. And this is how you can do it. This is one way of doing it, actually. That's why it's called a gated D latch. Basically, you really want to write a data value, right? You don't really care about this SNR. You want to write, you want to say, I want Q to be 1 or 0. And that's the data value over here. And you want to be able to say, sometimes I want to change the value. Other times I don't care, I don't want to change the value. So you have 2 input signals now. D, data value that you want to write, and the write enable signal saying, I want to write this data value. So if write enable value is set to 1, input is set to 1, then Q should get the D value. I don't really care about what these are. Those are internal signals now. If write enable signal is set to 0, Q should keep the prior value it was set to. Makes sense, right? That's the basic storage element now. And now I don't care about RNS. In fact, I made sure that they're not going to be 1 at the same time or 0 at the same time. We'll see in that logic, you can see something over here. Basically, Q takes the value of D when write enable is set to 1. You can convince yourself to do that with that. So if write enable is 1, then what matters is this D dominates. Basically, if D is, let's say 0, for example, this becomes 1. And well, let's say D1 over here. If D is 1, this becomes 0, and this becomes 1. That's the easier way of looking at it, right? If D is 1 and write enable is 1, let's take a look over here. This becomes 1 over here because you see that this is D bar. And this becomes, wait a second. So, okay, I want to write 0. Let's start again. Write enable is 1. D is 0. This becomes a 1. And because of the, okay, what am I doing wrong? Sorry. See, you can easily get confused over here. So let's say, okay, let's say write enable is 1 over here, right? You want to write. And you want to pass the D value over here of 0. Okay, you want to pass the D value of 1 over here if you want to write 1. So this, both of them are 1. This becomes a 0. Okay, now Q becomes a 1, right? That's exactly what we want. If write enable is 1 and we want to pass the D value of 0, now it's better to take a look at this over here because this does exactly opposite. Write enable is 1. D is equal to 0 over here. So this becomes a 0 over here, and this becomes a 1. So Q bar is a 1, and Q becomes 0 again. So if you want to write 0, that's how you write 0. So basically, that you can construct a truth table that way. And SNR now can never be 0 at the same time. Why? Because they're dependent on only D and right enable. And clearly, they cannot be 0 at the same time if you actually follow the logic over here. So hopefully that makes sense. So let's take a look at the truth table of this. So now the truth table is you have 2 inputs only, right enable and D, and output is Q. If, as I said, if right enable is 0, it doesn't matter what the D value is. You're not going to write the D value over here. As a result, Q maintains what was previously written. If right enable is 1, Q receives the value of D. And we just showed that Q received the value of D. Makes sense, right? And now you can convince that SNR can never be set to 0 from the outside. Okay? Okay, so that's the gated D latch. Any questions on this one? Yes. So excellent. Basically, I think your bigger question is this metastability issue. Can that lead to a random number generator? And the answer is yes, absolutely. Actually, assuming that the variation in the circuit is random, then you can actually generate random bits, basically that way. And this could be one way of generating random numbers. There's actually a lot of literature on that topic. Okay, now you're using a circuit to generate a random number. That's another thing that you can do, as you can see with the circuits, but we're not going to use that for that purpose. Okay, so this is clear, right? Gated D latch. Now we have forbidden people to set SNR to 1, but now we at the cost of additional 2 additional NAND gates, right? That's the downside. Okay, so now let's talk about the concept of a register. So how can we use D latches to store more data? Basically, this is our D latch, and this is our right enable signal, as we discussed. If you don't want to store only 1 bit, but you want to store 4 bits, well, use more D latches, put them in parallel, and they can operate at the same time. So if you want a 4-bit value, for example, their right enable signal can be shared, but they may have different data bits inputs into the latches. Okay, so that's what this says. Hopefully this is easy, and this is represented. Basically, it's called a register, a structure that stores more than 1 bit and can be read from and written to, as you can see. And this register holds 4 bits in this case, and there's a notation that says output is Q 3 through 0. This means you have basically bits 3 through 0, and that's 4 bits. If you had, for example, 16 bits, that would be Q 15 through 0. 32 bits, Q 31 through 0. You will see this notation a lot when we talk about Verilog, for example, next week. And this can be abstracted this way. This 4-bit register has a single right enable signal, a 4-bit data input, and 4-bit data output, whatever the current state is inside there. Okay, now we're going to build memory out of these registers, actually, or similar to registers. So let's talk about memory. Memory is really comprised of locations that you can write to or read from. So let's take a look at an example abstract memory array. Somehow that didn't work. Okay. So basically you have four locations in this case, 4 addresses. Every unique location is indexed with a unique address. We call it an address. And if you have 4 locations, you require 2 address bits, right? That's what it, so you need 2-bit addresses to actually specify 4 locations in memory. This is clearly a very small memory. Today's memories have billions of locations. But in each location, you may store 8 bits. So if you look over here, there are 8 bits. So this is an 8-bit register, basically. You can think of it that way. And this is called addressability, the number of bits of information stored in each location. And you can read the rest. Addressability is 8 bits over here. And the entire set of unique locations in memory is referred to as the address space. This is just for your information. Whenever someone says you have an address space of 4, that's what we see over here. And you have an addressability of 8 bits, that's what we see over here. And if you have an address space of 4, then the addresses should be log 2 to the 4 size bits. Typically, memory is much larger, and I don't need to tell you that clearly. Now, let's take a look at how we actually form this memory. Let's implement a simple memory array. This is going to be very simple. 3-bit addressability and an address space of 2, meaning you have 2 locations. So you need an address, 1-bit address, and each location contains 3 bits so that we can fit it on the slide, for example, and follow it more easily. Okay, so we're going to start with 1 bit. This is our gated D latch. And we're going to basically replicate it. We're going to make 6 of those. But now we need to somehow connect the addresses to it. So if you have an address 0, the gated D latch over here should be enabled so that we can read from them. If you have an address 1, gated D latches over here should be enabled so that we can read from them. Okay, so it's going to be easy, hopefully. The question is, how do you enable the top locations, the top 3 bits, or the bottom 3 bits? Or the bits, the top part is basically specified with address 0, the bottom part is specified with address 1. So because there are 2 addresses, as I said, address size is log 2 to the 2, which is 1 bit. Now these are the locations that I'm putting, and this is our basic memory that enables us to read. So what have I done here? This is the address bit. There's only 1 bit. And the top location is, you read the top location if this address bit is 0. If this address bit is 1, you read the bottom location. And this is called a word line. Basically, if the address bit is 0, this word line is enabled. If the address bit is 1, this word line is enabled. So this is called an address decoder. Basically, you have 1 to 2 decoder over here. Remember the decoder? We saw examples of it. Based on the input pattern, 0 or 1, you enable one output or the other. That's what we're doing over here. And that's exactly what we want to do. Remember when we talked about decoder yesterday, I told you that you can use it to decode addresses. Okay, that's exactly what we're doing right now. But there's something else we know over here. This is actually a multiplexer together with the decoder. Basically, if the address bit is 0, this becomes a 1, this word line becomes a 1. And the output of this OR gate, this AND gate, is dependent on the value that's stored here. And that drives this OR gate. And this address becomes a 0 because it's a decoder. And the output of this is 0. Basically, the output of this data value is dependent, when the address is 0, the output of this data value is dependent on whatever comes out of this bit. Makes sense, right? And that's essentially multiplexing. This structure together with this structure is really multiplexing the value based on the address. Address is your select bit, and the 2 data bits are actually data bits stored here and here. So you can convince yourself. And clearly, these are actually operate exactly the same way. So remember, because it's a decoder, only one word line is enabled, either this or this. So if the address is 0, you get the value of this gated D latch in this output, and this gated D latch in this output, and this gated D latch in this output. If the address was 1, you get the value of this gated D latch in this output, this gated D latch in this output, and this gated D latch in this output. Makes sense, right? Again, this is complete logic. We've already seen the decoder and multiplexer. The multiplexer may not look like a multiplexer because multiplexer is really this. The select line is coming from here. Select line is the address line, and the data lines are this. So just to jog your memory, this is how a multiplexer exactly works. Select line. If the address is 0, you take the top part. If the address is 1, you take the bottom part. And you can actually invert or rotate this multiplexer that we have seen and convince yourself that this S is actually the address bit over here. Sorry. And this is the inversion that you see right here, actually. Okay. Okay, so hopefully that's clear. We're going to actually build a bigger memory right now if my computer lets me move to the next slide. But before that, we want to be able to write to the memory also. I just show you how to read from memory. Writing to memory, again, very similar. We need to select an address and write to it. Oh, wow. Okay. Okay. Basically, we use the write enable bit. We've already seen this write enable bit. We're going to add that. And basically, if this address is 0 and write enable is 1, then the data value propagates into the output over here. Just like we've seen in the operation of the D latch. We've already seen that. If this address is 1 and the write enable is 1, then the data value over here gets written here. And we've already seen the operation of the gated D latch. That's how it should operate. And that's how it should work. And again, because the write enable is ANDed with the address value, that's how you ensure that this is the write enable signal of the gated D latch, basically. When do you write to this gated D latch? If the address is 0 and write enable is 1, if you're writing to memory. That's true also for here, also for here. If the when do you write to this gated D latch? If the address is 1 and write enable is 1. That's why you enable the write enable signal of this gated D latch and this gated D latch and this gated D latch. So this is the write circuitry. Before I showed you the read circuitry, this is the write circuitry. And hopefully they all work. Now, if you put it all together, you need to have the read circuitry and the write circuitry together. And I just put them together over here. I didn't add any magic, but basically, this is the write-enabled circuitry that we added. And this is the read circuitry that we showed earlier. Now, this is a 2-location memory array where each location stores 3 bits. And you can write to it and you can read from it. It's beautiful. This basically, you can also now draw the transistor level implementation of it, right? Because we basically started with a transistor and built up everything. There should be no gap in knowledge over here. Okay, now let's take a look at a bigger memory array. So how do you make it bigger? Well, if you want to make it, so this is 2 locations and each location 3 bits. If you want 4 locations and each location 3 bits, that's it. You make the decoder bigger, you make the multiplexer bigger. That's the idea. Okay, wait a second, it's moving too fast for me. So this is the decoder. Now, because you have 4 locations, you need to have 2 address bits. And how do you decode the address? A 2 to 4 decoder. This is exactly a 2 to 4 decoder, right? And then how do you multiplex the data that you're reading? Your select line is the output. Basically, it's a 4-to-1 multiplexer because there are 4 locations to read from. And you want to read one of them. So you have a 4-to-1 multiplexer over here. And the select lines of the multiplexers are really dictated by these. These are really forming the, these are really the select inputs. The addresses are really the select inputs, basically. Does that make sense? Yes, please. I just made it up. Yeah, it could have been just 1 bit. It could have been 8 bits. A more realistic one would be 8 bits, but I just wanted to be consistent with your book. The book, Patel and Patel actually has exactly the same example. But it could be, basically, you see that the different bits are operating exactly the same way, right? They're connected to the same write-enabled signal, as well as the same address word line. Makes sense, right? So you could actually extend this to 64 bits or 10,000 bits. So you can have 4 locations where each location stores 10,000 bits. Yes? Oh, so don't worry about that right now. So this is not DRAM. So this is not vulnerable to RowHammer as much as DRAM is. But now you're thinking exactly. So if you want to actually map it to what we discussed, this is exactly a row basically. That word line is actually a row of memory, and we will see that in DRAM it's 8 kilobytes. So very good mapping. Okay, so convince yourself that this works. Basically, there's no knowledge gaps so far. But if you look at your book, it also shows reading location 3. So if you want to read location 3, your address should be 11. It enables reading. Write enables is 0, so you should not write into the latch. And this multiplexer selects this data bit. This multiplexer selects this data bit. This multiplexer selects this data bit. So you read these 3 bits in parallel in that location. Your address needs to be 11. Your enable needs to be 0 because you're not writing, you're reading from the location. So recall the decoder. So does this look very familiar to you? It does, right? Well, I should go back here. This is your decoder, basically. That's the address decoder. It looks exactly the same as this one. Maybe some bubbles are turned around. Okay, recall the multiplexer. This is essentially what we're seeing. I wish I could do this, but basically, the multiplexer is essentially these purple things over here. These purple things, plus, of course, these ones over here that are not highlighted, are really the multiplexer. Okay, so this is a 4-to-1 multiplexer. We just use these 2 plus the gated D latch and connected them together to form memory and replicated them to form memory. Okay, let me see. Let me finish this and then we're going to take a break. This is going to be very quick. But now we've built memory. That's great. We're going to soon start sequential logic after this and finite state machines. But let's talk about implementing logic functions using memory also. Remember, we use multiplexers to implement logic functions. We use decoders to implement logic functions. Now we built memories out of multiplexers, decoders, and gated D latch. You can still implement logic functions with memory. I think this is fun, actually. This is really amazing. So this is our bigger memory array. It's a it's basically 4 locations, right? Let's assume that you want to implement a logic function. This is your logic function, and everybody recognizes what this is, right? It's an AND function. How do you implement it? Well, you have 4 memory locations. Each of them stores the bit you want in the output, 0, 0, 0, 1, and inputs are the address bits, which is the 2 to 4 decoder over here. But basically, you can implement an AND function by storing 0, 0, 0, 1 over here. And when you have address 0, 0, you get a 0. When you have address 0, 1, you get a 0. When you have address 1, 0, you get a 0. When you have address 1, 1, you get a 1. And that's your AND function, basically. This is essentially a lookup table. And a 2 to the n location n-bit memory can perform any n-input, m-output function. It's beautiful. It's expensive, clearly, for AND. But if you want to really build a much more sophisticated function, for example, I don't know, square root, it may be not that expensive. Not as expensive as really building a square root in combinational logic. So memory array is used to perform logic functions in this particular case. And each address is the row in the truth table. Each data bit is the corresponding output value. Makes sense, right? I find this really beautiful. Okay, so lookup tables are commonly used in FPGAs, and this sort of lookup tables are also used in FPGAs, similar to the multiplexers. And I'm not going to go through this. Your H&H chapter actually has kind of a nice explanation of an old FPGA, and you can read it, but it's completely optional. You don't need to read it. But know that these lookup tables are actually used in real systems. Okay, so this is a great place to stop and take a break, and we're going to get back with the bell. We're going to talk about sequential logic circuits.
I have a question about Apple's new chip.
Okay, I may not be able to answer because I may not know.
Yeah, I guess. They have 128 gigabytes of RAM.
That's right, yes.
Yeah, and how do they guarantee fast access to such a big amount of storage?
Well, it depends on what you mean fast, of course, right? It's much slower than the caches, of course.
Yeah, maybe do they take SRAM or something?
Oh, no.
DRAM or
yeah, we will see the memory hierarchy, but they try to cache as much as possible inside the SRAM, of course. But of course, SRAM is limited size, right, in their chip. So in the end, if they need to go to DRAM, they will pay the latency cost, and it will be long latency.
They have a higher latency with 128 gigabyte and
64 gigabytes. So that's a very good question, actually. The raw device latencies are not higher, and they have more channels. So they may have higher latencies because they may have more requests coming from because the amount of increase in the core counts is higher than the amount of increase in the memory bandwidth, if I understand correctly, based on their prior chip. So I believe they will have higher latencies, yes.
Okay, but not.
It's not because of the higher latencies inherent to the memory itself, because they're not increasing the size of each memory module. They're just adding more memory modules.
Okay, but they can compensate it with a higher amount of cache. So you
potentially,
don't
yes.
it while using.
Potentially, yes. If they're doing very good caching, if the workload is amenable to caching, yes, they can potentially compensate it. Yes.
Good. Thank you.
Sure, you're welcome. No. Okay. So let's continue. I will get back to where we left off, but I will mention one thing before we continue, because some of your colleagues who are doing the readings realize that Harris and Harris has a different SR latch, and that's true. I forgot to mention it. This is SR latch can be built based on cross-coupled NAND gates, which is this case, or cross-coupled NOR gates. And you can convince yourself they actually operate similarly, but the inputs may need to be a little bit different. The truth table is clearly different, right? Because cross-coupled NOR is different from cross-coupled NAND. But your Harris and Harris books talks about cross-coupled NOR. I find cross-coupled NAND a bit easier to explain things, but again, this is just a choice, right? So if you read Pat and Patel, they talk about cross-coupled NAND. Okay, so I wanted to clarify that. So hopefully that's clear. In the end, the basic operation, there's nothing, in the fundamental operation, there's nothing different between cross-coupled NOR and cross-coupled NAND. Okay. In the end, they're both operating based on the cross-coupled inverter principles. Okay, any questions? Any other questions that anybody wants answered in a burning way? Okay, I don't see anything. So let's move on to sequential logic circuits. Now you know how to build memories. That's great. What can we use these memories for? And now we're going to build logic circuits that can do things like controlling traffic lights, or giving you, I don't know, a vending machine controller. I'm not going to cover that, but you can find that in your book, Pat and Patel, for example. Okay, so what's a sequential logic circuit? Basically, I've already said this. We examine circuit elements that can store information. Now we will use these to build circuits that can remember past inputs and operate on past inputs. And the way I like, the analogy I like in terms of sequential logic circuits is this versus this. Okay, has anybody used this combinational lock? How many people? Okay, a lot of people, that's good. Has anybody used this sequential lock? It's also called, in English at least, it's called combination lock. It's really kind of annoying terminology, but okay, I think more people have used the first one, right? Can I see a show of hands for combinational on this one over here? Okay, what about sequential? Okay, I think sequential is losing. So basically, these are two different types of locks, but I think the analogy is very nice. If you look at this lock, the output, meaning output, there's only one bit output over here, whether this is open or closed, right? The output depends only on the current inputs. Basically, whatever you put over here, at least in most incarnations of this thing that I have seen. Basically, you put 0, 0, 0, 0, it doesn't open. You put 1, 1, 1, 1, it doesn't open. You have to figure out what the value is that is required to make it open. But it doesn't remember what you did previously, right? You may have put 1,000 different numbers and you may have been unsuccessful. It doesn't remember. As long as you put the correct number at a given point in time, you get it open. This is a combinational circuit. This is sequential because this operates based on fundamentally different principles, meaning this remembers what you have done. So to be able to open this, you need to take a sequence of actions. You need to turn it to the right and find the right number. You need to turn it to the left, find the right number. You need to turn to the right again, for example, find the right number. If you do something wrong at any point in time, it goes back to the original state, and you have to do things correct from the start again. So basically, this is a sequential circuit. It remembers what you have done, and it's the next state is basically dependent on what you have done and what you have inputted. What you're inputting right now, as well as what you have done in the past. So let's take a look at the sequential circuit a bit, because we're going to build a state diagram of it. So as I said earlier, anything in the world, in my opinion, you can build a state diagram of. You just need to know the inputs, outputs, and the states. Here, we know all of them, actually. So let's talk about the notion of state, though, because this is very fundamental to any aspect of life and engineering, especially. So in order for this lock to work, it has to keep track of past events, meaning remember them. So for example, if passcode is R13, meaning turn it to the right to the value 13, turn to the left to the value 22, and turn to the right again to the value 3, the sequence of states to unlock this needs to be the following. Initially, the lock is not open, it's locked, and no relevant operations have been performed. This is one state. This could be in, right? When you actually turn it to right to the 13, you could get to another state where it's locked, but the user has completed R13. So user has made some progress in the right direction. And then if the user inputs L22, it's still locked, but the user has completed a sequence of R13 and left 22. And then if the user inputs R3, meaning turns it right to 3 while you're in this state, then the user has completed the right sequence of events, and this becomes unlocked. So the output becomes unlocked or 0. You can represent unlocked with 0, for example, or 1. Your choice. So basically, there are 4 states in this case. We'll see the state diagram in a little bit. The state of a system is really a snapshot of all relevant elements of the system at the moment of the snapshot. Maybe this is a mouthful, but basically, to open the lock, states A through D must be completed in order. If you make a mistake at any point, like anything else happens, if you turn left 5, for example, for some reason, the lock returns to state A. So you need to start over. Makes sense, right? Of course, you can build a different lock that operates in a different principle, a different state diagram. But I'm describing the state diagram of reasonably commonly used sequential locks. So that's the notion of state, basically. This is what state means. Snapshot of all relevant elements of the system, right? And you can describe a state like what we have described over here, right? These are distinct states, A, B, C, D. You can have more states also, right, if you want. But this is the state diagram, basically. This is the state diagram of our sequential lock. It completely describes the operation of the sequential lock. You do not have anything like this for the combinational lock. Why? Because it doesn't have states. At this point, you apply some inputs. Based on those inputs, it's either open or closed. That's the only state it can be in, basically. It doesn't remember anything else. There's no notion of state there, right? But here, there are 4 distinct states, as I described earlier, right? And you can describe it with, we're going to use these state diagrams to describe finite state machines or sequential circuits. And this is a locked state. This is the output. This is also called a Moore machine, actually, where the output is a function of the state. And there are 3 locked states and 1 unlocked or open states. And you can see that you can transition from state to state. If you're in state A, locked state over here, if you get an input R13, right 13, you go to state B. If you get anything other than R13, you stay in state A. The system stays in state A. And then if you get input left 22, if you're in the state, you go here. If you get any other thing than L22, the system goes back to A. I've already described this, so I'm not going to go through it. Basically, this completely describes the possible states and the transitions of the states of that sequential lock. Meaning, this sequential lock is a circuit. You can think of it that way. And we're completely describing our circuits. We're not missing out anything. Well, actually, there's something missing out, which is there's a reset state. There should be a reset input, which goes to the lock state when you lock it, actually. But basically, where do you start from is the key question, right? That's what's missing out in the state diagram. You should never miss that out in a computer circuit. Here, it depends on basically what you have done with the lock, locked or unlocked, but we're not going to cover that. Okay, so there's another thing that's interesting here that we're not going to see much more in this course. This is actually a very asynchronous state diagram. So we'll understand state diagrams fully later today. But this sequential lock is a bit different from computers. The state changes happen asynchronously. We can think of it as an asynchronous machine. State transitions occur when they occur, meaning when the user inputs something, state transitions occur. There's nothing that synchronizes when each transition must occur. Computers are not usually built that way. Most modern computers are synchronous machines. What does this mean? State transitions take place after fixed units of time, dictated by a clock, as we will see in part. So whenever you talk about for example, 1 gigahertz machine, 1 gigahertz indicates the frequency of the clock, how frequently the clock changes. And a clock cycle is basically how frequently the clock goes from completes one cycle. And state transitions happen at the beginning of the cycle. Why is this done synchronously? To ease the design of a complicated machine. There's no reason why you cannot design an asynchronous computer, actually. People are working on it, but it's very difficult to design, it turns out. These are 2 different design paradigms with trade-offs. We're going to assume clocked systems going forward, and I'm going to give you an example of that right away almost. Okay, but keep in mind that we're going to talk about synchronous systems with clocks, but this doesn't mean that you cannot design asynchronous systems as well. We're going to get back to the slide in a little bit after we see the notion of clock. Okay, so another simple example of state. Again, I'm not going to talk about computers. I'm going to give you an example from a standard Swiss traffic light. So hopefully everybody here knows that a standard Swiss traffic light has 4 states, and hopefully that hasn't changed recently. So there's a green state, right? That's nice. Yellow state, red state, and the 4th state is this, red and yellow. Get ready to go, basically, right? So these are 4 distinct states. And this is a state machine. I'm going to simplify things a little bit. I'm going to assume you stay the same amount in each state, meaning, well, I don't know, 5 seconds here, 5 seconds here, 5 seconds here, 5 seconds here. You can generalize what we built, actually. It's not that hard. But the sequence of states are always as follows, right? You have state A. This could be state A, and then you go to state B, and then you go to state C, and then you go to state D, and then you go back to state A. And assume that you stay in each state an equal amount of time. How do you move from one state to another state? There's no input, right, in this particular case. You have to have some notion of time. You have to have a synchronizer, basically. Time is synchronization in the end, right? So that's where we need the notion of a clock, right? Because there are a lot of examples like this where you need a notion of time that is real, and clock comes in. Actually, it's very interesting. If you go to the philosophy of time, you really need to, what is time is a very fundamental question in the end, right? What are clocks? Actually, physicists and philosophers actually talk a lot about this, which we're not going to talk about. We're going to assume a clock exists. And it determines a real time that we can think about. So when should the light change from one state to another? We need a synchronizer or clock to dictate when the states should change. And this is basically a signal. There's some oscillator that generates a signal, and the clock goes from 0 to 1, and then stayed as 1, and then goes from 1 to 0, and then stays as 0. This is one clock cycle. And then clock repeats that. So I will animate this again, like forever, basically, while the system is in operation. Okay, this is another way of looking at it, basically. This is from Pat and Patel. One clock cycle is this. So during that clock cycle, state doesn't change. You stay in state A, which is the green light. At the end of the clock cycle, or at the beginning of the next clock cycle, you go to the next state, which was the yellow light, right? That's good, I remember that. Yellow light. And then you stay, the light stays yellow for this clock cycle, and then at the beginning of the next clock cycle, it becomes red, right? You can keep doing it, basically. It keeps continuing. Does that make sense? So that's why you need the notion of a clock, because you need some notion of time. And all synchronous systems use clock. So let's take a look at this a bit more. At the start of the clock cycle, when clock goes from 0 to 1, system state changes. During the clock cycle, the state stays constant. And we will see how important this is later on. So in this particular case, this is important because you don't want to change the state, right? In the middle of the state A, you don't want to go to red, for example, right? It's green and you don't want to keep changing. In systems, in real systems like we will see, that's the same thing, basically. If you build a processor, you have one state, and during that state, you're operating with the values of that state, and there's some combinational logic that evaluates. For example, you're doing some addition, and it needs time to finish. And that time is dictated by the clock cycle. Meaning, you need to set your clock cycle long enough so that that combinational logic can finish its operation so that you can move to the next state. This will become much more clear when we talk about timing and verification. But this clock cycle is really important so that you can design your combinational logic so it can finish what it needs to do within a clock cycle. So in the Swiss traffic light example, we assumed it's 5 seconds, right? But when you design a microprocessor, you usually have a target. Okay, I'm going to have a 10 gigahertz machine. 10 gigahertz machine has a clock cycle of 0.1 nanoseconds. 1 gigahertz is 1 nanosecond, 10 gigahertz of 0.1 nanoseconds. So I have 0.1 nanoseconds to finish work and then go to the next state. So you cannot have any combinational logic that takes more than 0.1 nanoseconds, because if you have it, the results are not available when the clock changes. If the result is not available, that combinational logic is useless. Well, it's actually wrong. It computed something that you couldn't capture. Right? Again, this will become more clear when we talk about timing and verification. That's why clock is so important. So when you set your clock cycle to that value, you should make sure your combinational logic finishes before the time that's dictated by that value, 10 gigahertz. Or you should extend your clock cycle. Or you should change your state diagram to account for the fact that combinational logic does not finish, and you cut the combinational logic and make sure the work that's needed to be done by that combinational logic is done in the next clock cycle. These are all things that you can play when you actually design a system. This will again become more clear when we talk about timing and verification. But that's how the notion of a clock works. Does that make sense? Okay. Okay. So the Swiss, this light is actually a very nice example, in my opinion. I have a funny story over here. Not all places in the world actually have this fourth state. Some places in the world actually are simpler. You have only 3 states. And when I was actually lecturing at Texas, I made the mistake of actually introducing this fourth state, and everybody gasped. They have no idea what this is, basically, because it doesn't exist, right? Their state machine is not designed that way. Their lights are not that way, basically. And you can figure out which parts of the world operate differently. Okay, but in the end, it's the same thing. That's another state machine, basically. And actually, if you really want to make this different, okay, maybe I'm getting ahead of myself, but for example, if you want to stay in state A 20 seconds, and state B 5 seconds, state C, I don't know, 5 seconds, and state D another 20 seconds, you can have one state over here where it's green. In the next clock cycle, you go to another state so that you can stay 5 more seconds. In the next clock cycle, you go to another state, you can stay 5 more seconds. In the next cycle, you can go to another state, you stay 5 more seconds. Now you stay 20 seconds. And then next clock cycle, you go to B. That's how you can stay 20 seconds when and the light is green. Right? You replicate the A state so that you stay in a replica of the A state 4 clock cycles. Makes sense, right? So basically, you can use the notion of time so that you can and change the state machine so that you can stay in a particular state different number of cycles and different amounts of time in the end. So it's beautiful. Okay, just let me summarize what a clock is. So clock is really a general mechanism that triggers transition from one state to another in a synchronous sequential circuit. In an asynchronous circuit, clock doesn't exist. And we've seen that in the sequential lock. But we're going to talk about synchronous circuits. Clock synchronizes state changes across many sequential circuit elements. So if you have tens of thousands of registers, all of them change state at the same time. And this is very powerful, actually, when you build a computer. And we will see this. Existing computers have billions, well, getting closer to trillions of transistors, right? That's a lot of actually sequential logic in there. So combinational logic evaluates for the length of the clock cycle, we said. So you need to make sure that your combinational logic finishes and produces the output it's supposed to produce before the clock cycle ends. And clock cycles should be chosen to accommodate maximum combinational circuit delay. That's what I just said, basically. I said it in a different way. So more on this later when we discuss timing. So timing is actually going to be an important lecture, even though I'm not going to question you on it on the exam or anywhere, actually. It's really important to make really systems work, that timing and verification lecture that we will have next Friday. Okay, so let's go back to this asynchronous versus synchronous state changes, right? So now we've seen a synchronous machine. State transitions take place after fixed units of time controlled by the clock. And these are 2 different design paradigms with trade-offs. We can talk about many trade-offs, but synchronous control is in general easier to get correct, especially when the system consists of many states, millions of states. You can think about synchronous control much more easily, basically. Everybody changes state at the same time. You have this conductor, it's conducting an orchestra. Orchestra consists of, I don't know, 100 musicians, and the conductor's baton actually goes down, and everybody figures out what state they should be in at that point in time, right? You can think of the clock as a conductor also. Okay, but asynchronous control, there's no clock, it doesn't exist, and it can be more efficient because there's no overhead of clock. So think about clock. Clock needs to actually be generated, clock needs to be propagated to all parts of a circuit, and clock needs to be propagated in similar amounts of time. And we'll see that in timing and verification. So there's actually a lot of clocking overhead. In fact, in the past, in some circuits, this clock generation and propagation consume maybe 30, 40% of the power of a chip. People have reduced that over time, but 30% of the, it's still significant power consumption of a chip, basically. Okay, so we will assume synchronous systems in most of this course, even though asynchronous systems may be possible. Actually, almost all computers that you use are synchronous systems because it's easier to design. But proponents of asynchronous systems always say, oh, asynchronous systems are much more efficient. Let's build them. It just becomes too difficult to build large systems. Okay, so now let's talk about finite state machines. Well, we kind of saw a finite state machine, actually. These are finite state machines. Let's formalize the notion a little bit. So what is a finite state machine formally? It's really a discrete time model of a stateful system, right? We talk about stateful systems. You have a discrete time model, and it's a pictorial model, actually. Each state represents a snapshot of a system at a given time. And an FSM pictorially shows the set of all possible states that the system can be in, how the system transitions from one state to another. Again, you can represent life with a finite state machine, except we don't have the capability to do that because we don't know all the, I don't believe we know all the inputs, or we can represent all the inputs. I don't believe we can represent all the states, and I don't believe we can represent all the outputs. Okay, so you can represent anything this way, in my opinion. Any stateful system, I should say. So an FSM can model clearly these things. A microprocessor. Later, we will see a finite state machine for a microprocessor that we're going to build. It's going to be much more complicated than the finite state machines that we're looking at right now. And it enables us to pictorially think of a stateful system using simple diagrams. So what does it consist of? 5 elements, basically. A finite number of states. It needs to be finite so that we can represent it, right? State, we already discussed what a state is, so I'm not going to repeat that again. A finite number of external inputs, a finite number of external outputs, an explicit specification of all state transitions, what should happen from this state to, in this state when it receives this input, which state do you transition into, how to get from one state to another, basically. An explicit specification of what determines each external output value. What is the output value, basically, that you see in a state or when you're transitioning between states? Okay, so we're going to see a finite state machine. We're actually going to build one. So it consists of 3 separate parts: next state logic, state register, and output logic. So we're going to look at each of them. And this is what a finite state machine looks like. This is a sequential system in the end. You have some inputs, you have some outputs, as you can see. There's some next state logic that looks at the current state. This is your state register, basically. Next state logic takes the current state and the inputs and produces the next state. And the clock, of course, right? Next state gets latched at the beginning of the clock cycle. And then output logic is based on the state in this particular case. This is a particular type of finite state machine called a Moore machine. Output logic can also be dependent on the state and the current inputs. That's called a Mealy machine. I don't really like memorizing this names of machines, but you can basically have output logic depend on just the state or state and the inputs. In this particular case, it's just on the state, as you can see. Okay, that's the state register I said already. And the key thing is at the beginning of the clock cycle, next state is latched into the state register. We're going to see that we don't have an element like this that we have talked about yet. So we're going to build a new element for this. Think about that, and I will show you that. So basically, finite state machines consist of sequential circuits, which are the state registers and input and output. So input is the next state, output is the current state. They store the current state and load the next state at the clock edge. So clock going from 0 to 1 also is called the clock edge. It's called the rising edge of the clock because you go from 0 to 1. Combinational circuits are the next state logic, which determines what the next state will be, and the output logic, which determines what the output should be. Okay. So let's talk about the sequential circuit, because as I said, we don't have this element. What we want from this element is it captures the next state when the clock goes from 0 to 1, and it doesn't change the state during the clock cycle. Unfortunately, whatever I showed you before doesn't satisfy this criteria. So let's talk about why. What happened here? Okay. Okay. So basically, we need 2 properties. We need to store data at the beginning of every clock cycle. Clock transition determines when the input is acquired and stored in the register. I'm going to call it a register for now. And the data must be available during the entire clock cycle. Basically, this register should not change its state during the entire clock cycle. Okay? Because, as I said, your state should not change, right? Your traffic light should not become red, for example, when it's supposed to be green. And your combination logic is designed to evaluate in the entire clock cycle. Okay, so let's take a look at this. This is the clock cycle. Well, each of this is a clock cycle. This is a clock cycle. Basically, you see the clock cycle boundaries. And if your register input looks like this, register output should look like this. Basically, you only, this is the state register input. This is basically the next state. You capture the next state at the rising edge of the clock cycle. This doesn't matter. This did not last enough for the rising edge, as you can see. And you capture the next state at the rising edge of the clock cycle. Basically, you don't capture it over here. You don't capture it over here. You don't change the state over here. You just basically do it synchronously, meaning at the rising edge of the clock cycle. That's the basic principle of operation of a synchronous machine. If you do it asynchronously to the clock, then there's no reason for a clock, right? Basically, you're violating the principle of the clock. Because we set the principle saying we're going to be synchronous to the clock. If you do it in some other way, then you're basically violating that basic principle. And why did we set that principle? Because there's a reason why we want to stay long enough in the state, because there's some combination logic that's evaluating. And if you capture some state earlier, that combination logic depends on the prior state that was stored or current state. And you're changing the current state while the combination logic is evaluating. So if you go back over here, well, actually here. Yeah, this is what the state looks like. So state, there's some combination logic. This combination logic is evaluating, and it's assuming that it has the entire clock cycle. But if you change the state over here, if next state becomes state or state becomes next state before the clock edge arrives, then the value changes over here, and the combination logic, let's say, doesn't get confused, but it starts evaluating something else. And you will get the wrong value at the end. Okay. So that you're violating the principles of synchrony, basically. Okay, so that's what we want. Hopefully that's clear. This is the desired behavior. Now let's take a look at whether the gated D latch provides this behavior. And the answer is it doesn't actually. And that's the problem with latches. We call the gated D latch, it looks like this. We cannot simply wire a clock to the wide enable of a latch. Remember, that's kind of what we want to do, right? The latch, the register wants, we want to change the register at the clock edge. And one way of doing it is by wiring the clock to the right enable. Okay, this is one way. You can try to do other ways, and you will fail, in my opinion. If you don't fail, let me know. But whenever the clock is high, the latch propagates D to Q, meaning whenever the clock is 1, right enable is 1, Q becomes D. This is not what we want, clearly, right? Because we don't want that behavior. If you go back to this picture, whenever the clock is high, we don't want the register input, in this case, we don't want this to propagate to the register output. So this should not be latched. But gated latch is exactly latching this one. Gated D latch is exactly latching that one. So clearly gated D latch is not working for us. This is also called the latch is transparent, meaning whenever the clock is high, it's transparently propagating the value at its input to its output. So let's take a look at this. I kind of showed you actually earlier. If your register input is like what we have seen earlier, your output will change like this. And this will affect your combination logic because this gets input to your combination logic inside your sequential circuit, right? Which is the next state logic or the output logic. It can actually affect your output because your output may be dependent on the state, right? It is actually in the Swiss traffic light. It's dependent on the state. Okay? Okay, so clearly this is not what we want. Also, this is not what we want. Your register input changes somewhere after the clock cycle, but that's not what we want. We really want that to change over here. Go to 0 at this point. If you go back 2 slides, well, yeah, 1 slide actually, you will see that. Again, why? Because you're messing up with the combination logic. There's some combination logic that's evaluating over here, and you're messing up with it by changing the state that's input to that combination logic. Okay, so this is undesirable, basically. The question is, how can we change the latch so that we create a desirable element with the properties that we want? What are the properties again? The input, or D, is observable at Q, output, only at the beginning of the next clock cycle. Basically, you store Q equals D only at the beginning of the clock cycle, at the rising edge of the clock, 0 to 1, when the clock is going from 0 to 1. And Q, meaning the output of the state register, is available for the full clock cycle without changing. And that's where we try to build a new storage element. Okay, I think I already said this. We need storage elements that allow us to read the current state throughout the current clock cycle and not write the next state values into the storage elements until the beginning of the next clock cycle. So that's where we come, why people have come up with what's called the D flip-flop. Interesting name, but I didn't name it. This is called a D flip-flop. And it has two properties: state change on clock edge, and data is available for a full cycle. And we're going to use D latches to build the D flip-flop. This is one way of building a D flip-flop. There are other flip-flops that are actually discussed in your readings. I'm not going to cover them, but you can read about them. And there are actually some slides that I have as backup slides. You can take a look at them. So we're going to have one D latch. This is exactly what we've seen. This is the gated D latch. And we're going to connect it to the next one. Now it's becoming costly, right? So why is it going to be this way? Well, you will see the operation basically. And then we're going to wire the clock over here. So when the clock is 1 over here, this is the right enable, remember? When the clock is 1 over here, Q gets whatever value is over here. But when the clock is 1 over here, the clock is 0 over here, this value doesn't change. Now this is interesting, right? Basically, you're kind of having this control. It's called master-slave in literature, but this D latch controls what gets propagated into the input of the second D latch, if you will. And when the clock is 0 over here, what happens is this right enable becomes 1, and this input D value, which is really the real next state, for example, a value, gets propagated over here, but it doesn't get propagated to the outputs, because when the clock is 0 over here, this becomes a 1, but this is 0, so right enable is 0. Makes sense, right? So now this has actually our desired properties. That's exactly what I said over here. When the clock is low, which is this part, this master propagates the value of D to the input of the slave, but Q is unchanged. Basically, you're not changing Q over here. Only when the clock is high, the slave latches D, meaning only when over here, the value that was propagated over here in the low period gets propagated into Q, and Q stores D only at that point in time. But that value cannot change during this time, because when clock is actually high over here, it's low, inverted clock is low over here. As a result, this other D value that may come cannot change the value of that. So this is exactly the behavior that we want, right? At the rising of the edge of the clock, basically, clock going from 0 to 1, Q gets assigned D, and that assignment doesn't change during the entire clock cycle. You can convince yourself of this one. But of course, this comes at extra cost. Now we just doubled our circuitry plus added an inverter for the clock rate. But this, and people have actually optimized flip-flops. We're not going to get into that, but this does the job for us, basically. This is what we will use as our basic element to build state registers. And I'm going to abstract it this way. This is called the D flip-flop, as I said. It has a data input. It has a Q output. It could have a Q bar output also, and it has a clock now. And whenever you see this, think of an implementation of it like this. Okay? Make sense? Okay, so we solved this transparency issue. And we can use D flip-flops to implement the state register. So this is also called a rising clock edge triggered flip-flop. There are many different types of flip-flops. We may see some of them in the Verilog lecture next week. They're also, you can actually change it so that it can actually operate on the falling clock edge. How do you do that? Well, have the clock inverted over here and remove the inverter from here. Then you basically have a falling clock edge triggered flip-flop. But ignore that for now. We just need one clock edge, and based on the definitions that I said so far, we want the state to be captured when the clock is going from 0 to 1, then we want a rising edge triggered flip-flop. It has two inputs, as you can see, clock and data input, and it has one output and the complement of it. And we represent it this way, but we can actually represent it this way also. Basically, this is a shortened representation of it. The function is the flip-flop samples D on the rising edge of the clock, positive edge of the clock. When the clock rises from 0 to 1, D passes through Q. And that's it. That's the only time. Otherwise, Q holds its previous value as we want. And Q changes only at the rising edge of the clock, meaning Q is stable, meaning output is stable during the entire clock cycle. And that's what we wanted as we discussed. This is called an edge-triggered state element. This is just for your benefit. I'm not going to test you on these edge-triggered blah, blah. But edge-triggered state element, because it captures data on the clock edge, whereas the latch we saw is a level-triggered state element. Basically, depending on the level, when the level of the clock is 1, it basically propagates the value, captures data. And we didn't want that, as we discussed. Okay, so now we can build a register. This is what we want. Now we can safely construct finite state machines the way we want them. We can have multiple parallel D flip-flops, each storing 1 bit. And this is basically that. There's no magic over here. We just replicated it so that we have 4 bits. And we can actually represent that compactly this way. This is a 4-bit register, D flip-flop based register. And you can see this notation we discussed earlier. This says that this wire has 4 bits. This output wire has 4 bits, and this is the notation. Okay. Okay, I think I already said this. Okay, internally it looks like this actually, which is essentially the replicated picture that we showed earlier for the D flip-flop. Okay, now let's talk more about finite state machines. Next state, we have this element that works. Now we can really build finite state machines. We said that next state is determined by the current state and the inputs. And as I already said, there are 2 finite state machines that differ in the output logic. One is the Moore machine. Outputs depend only on the current state, as I said. But here pictorially, I show the difference between Mealy machine and the Moore machine. In the Mealy machine, outputs depend on the current state and the inputs. If we get to it, there's an exercise at the end in the later part of the slides where we can design a Moore machine or a Mealy machine. You can also read it in your book. It's the smiling snail, basically. Snail reads some pattern and smiles if it sees some pattern. I know who comes up with these patterns, but that's the smiling snail. Okay, if we get to it. Probably we're not going to get to it today, and I'm going to leave that with you. But we're going to get to one finite state machine example, which is also in your book. So if you don't follow this, don't worry. It's not my favorite example, frankly, because it's called a smart traffic light controller, but it's not very smart. You don't want to be driving in traffic where you have traffic light controllers like this. You will see what I mean soon. But basically, you have these traffic lights, as you can see, TA and TB. No, traffic lights, let's say. I think light A and light B, I should say. And light A is replicated on Academic Avenue, and light B is replicated on the Bravada Avenue. And you have 2 inputs, traffic sensors, TA and TB. Basically, these are true when there's traffic in the corresponding boulevards or avenues. And you have 2 outputs where the lights could be red, yellow, and green, 2 different kinds of lights. State can change every seconds, basically. Normally, state changes every second. Basically, clock cycle is 5 seconds, every 5 seconds, I should say. Except if the state is green and the traffic sensor says there's still traffic coming on this avenue. So this is not very smart, as you can see, right? But it's in your book, so you can follow it easily. Why is it not very smart? Because if for example, the light is green over here and Academic Avenue is congested, the light always stays green. And you don't want that behavior from a smart traffic light. But I've driven through smart traffic lights before, and they're not always smart. But they're not as bad as this one, I think, unless they're broken. Okay, so basically, this is our black box of the finite state machine. Let's design this finite state machine very quickly. I'm going to do it quickly because you can actually read it in your book also relatively easily. But this is our traffic light controller. These are the inputs, TA, TB. There's reset. You start from some state. There's clock. And these are the outputs, basically state of the lights in this current cycle, LA and LB. And clock is 5 seconds, basically. Clock cycle is 5 seconds. Okay, I already said this, I think. Outputs, I already said this. So let's take a look at the transition diagram of this. We're going to use Moore FSM, meaning outputs are labeled in each state. States are circles, and transitions are arcs. Initially, we start from some state. Academic Avenue gets the green, and Bravada Avenue gets the red light. Too bad for the people over here. And then if for example, if there's no traffic in the Academic Avenue, you transition to S1 state where Academic Avenue becomes yellow and Bravada Avenue still stays red. If there's traffic that keeps coming on the Academic Avenue, you stay in state 0. Okay. And then transition from state 1 to state 2 is unconditional, meaning at the edge of the next clock cycle, you go to Academic Avenue becoming red and Bravada Avenue becoming green. And then depending on the state of the input, which is traffic on the Bravada Avenue, you either go to state 3 or stay in the state. And then another unconditional transition at the clock edge happens from state 3 and state 0. Basically, this complete describes what we want, assuming this is what you want, and this is what your book wants. Okay, now we can build everything that we discussed. Let's start with the state transition table. We have the state diagram. This is our current state. Next state is dependent on the current state as well as the inputs, right? Now you can actually encode this next state. Just by looking at this, you can create the state transition table. I'm not going to do that, but for example, if you're in state 2, and if there's no traffic, this is state 2. If there's no traffic on B avenue, it doesn't matter what you have, whether you have traffic on A avenue, you go to state 3. If you're in state 2, and if there's traffic on the B avenue, you stay in state 2. It doesn't matter what whether there's traffic on the A avenue. Now, assume some kind of state encoding. We are encoding the states because there are 4 states. You need 2 bits to encode the states, meaning your state register is 2 bits wide. Now you can complete this truth table. Now you have 1s and 0s, meaning these are your current state, inputs, and next state. So you have 4 inputs over here, and you have 2 outputs, and you can determine the function. So what is S1? Next state, S1 prime. You can do everything that we discussed in combinational logic lectures. Figure out when this function is 1, and then write an equation. And you can do that easily. I'm not going to do that again because we've done it multiple times. What is S0, which is the next bit in the state encoding? And then you can basically figure that out also. Okay, why is it going so fast? Yeah, that's this. And now you can actually go and simplify each of them. You figure out that this is S1 XOR S0, which is current state bits. And this is actually based on the TA and TB inputs. It just happens because based on the state encoding that we assigned over here. If you assign different state encoding, your functions will be slightly different, basically. Does this make sense? Basically, this is everything that we discussed earlier. This is combinational logic. You need to determine your next state based on current state and inputs, and that's combinational logic, and you can optimize this combinational logic. Okay, output table, similar thing. Your outputs are dependent on the current state in this particular case. You construct a truth table based on your outputs on the lights, and you need to give an output encoding. Green, yellow, red need to have some encoding because we're dealing with bits, right? And there are 3 states, so you need to have 2 bits. You cannot represent 3 states with 1 bit. Okay, and then these are your outputs. Basically, each of the lights have 2 bits, as you can see. Now, basically, you do the same thing that we have seen earlier. You express LA1 as a Boolean expression of current state bits, and LA0, LB1, LB0. And these are the functions, basically. Okay? This is the combinational logic that's needed to generate outputs based on the current state bits. Now our schematic is complete. Basically, this is we looked at the next state logic. We figured that out. We looked at the output logic. We figured it out. That's it. That's all you need. Now we have the state register. We have 2 bits because we have 4 states. These are the current states. These are the next states that are going to be generated. Let's generate them. Okay, yeah, something is going really fast. Okay, so this is the next state logic. These are the current state bits. These are the inputs, TA and TB, based on the truth tables that we showed earlier. This is the logic that's needed for the next state logic. Simple. And at the rising clock edge, this combinational logic produces S1 bar and S0 bar, and that gets latched into the next state register. And then that's your current state for the next clock cycle. Okay, and the output is basically, we already figured that out also. That's dependent only on S1 and S0 because it's a Moore type machine. And this is your output logic. And we already figured that out in the previous slides. Okay, timing diagram, I'm going to let you figure that out. It's not important, but you can find it actually in the book. But basically, this basically shows you some timing as to what happens. How do you go from state to state? But I think this is obvious, actually. It doesn't really talk about timing. You can basically traverse the timing, right? This is logical. Let's talk about state encoding very quickly if we have time. Okay, very quickly. So how do you encode these state bits is also important. There are actually 3 ways of doing it: fully encoding, one-hot encoding, output encoding. So clearly we have 4 states. The fully encoding one actually is called binary encoding. You use the minimum possible bits. That's what we did earlier. 2 bits and 4 states, right? Okay, that's one way. This minimizes the flip-flops, but not necessarily something else. One-hot encoding is a different way. It's not basic example state encoding is basically you have 4 different bits, And each of them becomes a 1 depending on the state. And only one of them becomes a 1. This is called 1 hot because only one bit is a 1 and everything else is 0. This is actually really the simplest design process, very automatable, but it maximizes the flip-flop. So it may not be desired. There's also another one, output encoding. Outputs are directly accessible, but you can actually read about this. Maybe we'll start with this one in the next lecture. And I will let you continue. In the end, it's a designer's choice, basically. Okay, this is where we'll stop. Have a nice weekend. And next week, we'll start here. Okay.